Now we're going to be looking at binary trees. A binary tree is a rooted tree where each node has 0, 1, or 2 children. What this means is that you start at the top at the root, and if you look down, you always see somewhere between 0 to 2 vertices below it. So let's start on the one on the left and ask, is this a binary tree? This is a single vertex. And that single vertex, if you look below it, it does indeed have 0, 1, or 2 children. So this is the case that is sometimes said to be 2 empty subtrees. Now let's look at the next graph. Start at the top. There are 2 children below it. Looking at the next point, there is 1 child below it. And finally, at the bottom, neither of these have any children. So in every case, you have 0, 1, or 2. How about the third one? Well, that root has 3 children below it, so it does not satisfy the 0, 1, or 2 condition. Finally, how about this complicated one on the right? Well, this one will be a binary tree. If you work your way down, at every point, you see either 0, 1, or 2 children. For example, if we look at that vertex, there are 2 children. If we look at this vertex, again, 2 children. Now, there's a few keywords from binary trees that you'll want to keep in mind. One of them is leaf. And a leaf is a vertex that has 0 children. Basically, they're the ones at the bottom. So here we have leaves. And on this last one, we have a bunch of leaves, and even at different levels. But you'll notice that all the things that I highlighted have no children below them. The next concept here is an internal vertex. Internal vertex is not a leaf, and looking at the graph on the right here, we see that there are 5 internal vertices. And if we had been looking for leaves, there are 1, 2, 3, 4, 5, 6 leaves. That's an interesting pattern. Let's look at one of the other graphs. Let's say the middle one. This has 1 leaf. Oh, here's another one. And then it has 1 or 2 internal vertices. Finally, a full binary tree. So a full binary tree means that as you work your way down it, if you're not at a leaf, there are always 2 children. So look at the second graph here. If we start at the top, that's not a leaf, there are indeed 2 children. If we go here, that is a leaf, so that's fine. The right-hand one, though, that only has 1 child. So that is not a full binary tree. But looking at the far right, there's an internal vertex, it has 2 children. Internal vertex, 2 children. Internal, 2 children. Internal, 2 children. Internal, 2 children. So everywhere you look on that graph, if you're not at a leaf, there are 2 children. And that again is known as a full binary tree. When we're looking at binary trees, a related concept is an ordered rooted tree. In an ordered rooted tree, you have some kind of label that gives you an order. And then you would read the tree in order of those. So looking at the graph on the left, the vertex 1, that's like the root. And then below it, we can go to 3, 4, 5, 6. And notice that on level 2, actually it's level 1, on this level, we went what you would expect, counting left to right, 2 to 3. But on the last level, the counting was out of order. This was not left to right, it actually started in the middle. So keep in mind, on an ordered tree, you may not actually follow the order you expect. Let's look at the one on the right. This is an ordered tree where it's ordered by alphabetical order. So that means Dave comes on the left because alphabetically it is earlier than Nancy. Beth comes on the left because alphabetically she is earlier than Fred. So that one on the right is an ordered rooted tree using alphabetical order.